All right, guys, so we're talking today, reviewing something that we've actually done already, but we're going to kind of focus on it specifically today. And that's what if we're doing these integrals where you have the inside's not so nice, right? You can tell that there's been a chain rule or something going on. Like this first example, we're integrating from 0 to 2 of x times x squared plus 1 cubed dx. Now, we had mentioned in a previous video that you could FOIL this out. I mean, you could multiply this out 3 times, then you could distribute the x and do it the normal way, which is just going to take forever. Or we can do a u substitution. The nice thing about doing u substitution with integrals is we can kind of shorten the amount of work that we do. And we do that by changing these limits that we're using, okay? And that's what this formula is walking you through. And I'm just going to show you some examples because I think the examples paint a lot better picture than the messy formula. So if I'm integrating from 0 to 2 of x times x squared plus 1 cubed dx, just like before, usually the easiest thing to do is let our u equal the inside, the x squared plus 1. That means that du is going to equal 2x dx. And I can kind of move things around. I want to leave the x over here because I have an x on the outside. So the only thing I want to move over is the 2. So I'm going to make this 1/2 du equals x dx. So now I can replace everything. I can rewrite the integral. I can write the integral, and instead of an x and a dx, I'm going to put a 1/2. I'm going to move that out front, and I'm going to put a du. I'm going to put that at the back. And then my u I can plug in for the x squared plus 1 right here. So that becomes u cubed. Now, before I rewrite this, what we would do in the past with our other integrals is we would integrate, and then we would take our x squared plus 1 and plug it back in. But when I'm doing definite integrals, like we mentioned before, I can change my limits right here. I can change my bound by plugging those into my u function. So if I plug in a 0, 0 squared plus 1 is 1. So that becomes my new lower bound. And if I plug in a 2, 2 squared plus 1 is 5. And that becomes my new upper bound. When I do that, I don't have to plug the u back in. This is my new function. I'm done. So now I just have to integrate. So 1/2 multiplied by u cubed becomes, u cubed becomes u to the 4th. And that means I've got to put a 1/4 out in front. And I'm going to integrate that from 1 to 5. So that means 1/2. And then I plug in the 5, so 1/4 times 5 to the 4th power minus 1/4 times 1 to the 4th power. So I end up, how far do we want to go? We might as well finish this out. So 1/2 times, let's see, 5 to the 4th is 625 over 4. Minus 1 to the 4th is just 1, so that's minus 1/4. So that becomes 1/2 times 624 fourths, which becomes, what, 624 eighths, which you plug it in your calculator and you get 78. Okay, I can check this just like before. But I can either plug in the original function or I can plug in the u function. Either way, I can check my answer. I just have to make sure to use, if I use my u function, I've got to use the correct limits of my integration. So let's just go math. We're doing, nope, math 9. Let's get out of here. Why am I on my math 9? And I'm going to do my original function from 0 to 2, just in case I messed up my integration somewhere. I'm going to go all the way back to the original function, and I'm just going to plug that one in. So 0 to 2 of x, and then we've got x squared plus 1. And that's all cubed dx. So I hit enter, and I get 78.00000001, which gives us our 78. There's just some weird rounding going on there. So not too bad, right? Again, you could have left this going from 0 to 2, and when you got down here to before you plugged stuff in right here, you would have to plug in that x squared plus 1 for the u, which is a mess. Don't do that. Just change your bounds, and it makes the problem a lot more reasonable to work with. Okay, so moving on to this next one. We're integrating from 1 to 6, x over root 2x minus 1. So we've got, this one's a little bit more messy. There's going to be a lot more algebra involved here, but let's go ahead and let's try our u being 2x minus 1, which means du is going to be 2 dx. Now, I don't have anything else in there, so when I move the 2 over, I've got 1/2 du equals dx. And that almost takes care of everything, except I have this problem. If I rewrite my integral, 1 to 6, this is x multiplied by 2x minus 1 raised to the half, right? dx. So I have my 2x minus 1. I have my dx. What I don't have is an x value. So what I have to do is I've got to take my u function and solve it for x so that I can get rid of that x. I'm trying to get rid of all my x's and plug in u's. So u equals 2x minus 1. I can solve that for x, and I end up with what? X equals u plus 1 divided by 2. Now I can plug that in for x. So this is going to be my u plus 1 over 2. This is going to be my u, and this is just going to be my du. So now I'm taking the integral of u plus 1 over 2 multiplied by 2x minus 1. Nope. What am I doing? Multiplied by u to the 1/2 du. Now I need my new bounds. Instead of 1 and 6, I'm going to plug those into my u function. So 2 times 1 is 2 minus 1 is 1. 2 times 6 is 12 minus 1 is 11. So here's my new function that I need to integrate. I don't have to worry about going back. I can just use this integration. I can just do this one right here. And let's clean this up a little bit. I'm going to take this u to the 1/2 and distribute it in. I'm going to distribute it to my u just because I've got a little bit of a mess. And this 2 on the bottom, I'm going to pull out front because I forgot my 1/2 with my du, didn't I? So I have my 1/2 from my du. So now I've got 1/2 on front. I'm going to pull another 1/2 out to the front because this 2 on the bottom. And then I can multiply that u to the -1. I'm going, something looks funny here. This is a -1/2. I can multiply it in. So u to the -1/2 times u just becomes u to the 1/2. U to the -1/2 times 1 is just u to the -1/2. And that 2 I've already moved to the outside, so I don't need to mess with that one. Now I can just integrate. So this is 1/4, and then u to the 1/2 becomes 2/3 u to the 3/2, plus u to the -1/2 becomes u to a positive 1/2, which means I get to put a 2 out in front. And I'm evaluating that from 1 to 11. So I've got 1/4 and then I'm going to plug in the 11. So 2/3 11 to the 3/2 plus 2 times 11 to the half minus 2/3 1 to the 3/2. I better put the bracket around there. Plus 2 times 1 to the 1/2. A whole bunch of messy stuff, right? And I'm going to what do we want to do? I don't really want to simplify this at all. So let's see what happens when I plug that into my calculator. So if I go back here, and let's just plug in my 1/4, and then I need, what did we get? 2/3. Let's 1/4. And then we've got, just to help us keep track of our numbers here, 2/3. And then I need 11 raised to the 3/2. And what else? Plus that 2 times 11, we can just make that 2, and then we can write that as square root 11, just to make it a little bit easier. And then I'm going to minus, nope, I'm not going to minus. I'm going to go over, then I'm going to minus. And I need to put my 2/3 plus 2, right? Because all of that is just going to, this becomes 2/3, this becomes 2 because of all those ones. 2/3 plus 2, and close my bracket. See what we get, 7.07212. So 7.07212. And again, if this was a free response, I would have stopped right there. I wouldn't have tried to plug it in. I would have just let that be my answer, okay? All right, evaluating 0 to pi-halves of sine x cosine to the 4th power x. Oh, I forgot a dx right here. Okay, so let's let u equal cosine x, which means du is going to equal negative sine x dx, which means that negative du equals sine x dx. So that gets rid of my sine, that gets rid of my cosine, and it gets rid of my x. Does it get rid of my x? Yeah, because that cosine is in my x, and it gets rid of my dx. So integral of negative sine, nope, let's see, cosine of, why am I plugging in cosine? I made my u my cosine. So I'm doing u to the 4th power. And then I want my du. I got to put my negative out in front. And then I've got to plug in 0 and pi-halves. So if I plug in my top, pi-halves, the cosine of pi-halves is 0. Whoops, eraser. The cosine of 0 is 1. But I have a little bit of an issue because my bigger number is supposed to be on top. So I've got to put the 0 here, the u to the 4th du. And this negative becomes a negative because I had to flip it over, which makes them a positive. So I've just got the integral from 0 to 1 of u to the 4th du. And the nice thing here is I got rid of all of that trig. All I'm left with is a normal function. So this just becomes u to the 5th, and I put 1/5 out in front, and I integrate from 0 to 1. When I plug in a 1, I get 1/5, 1 to the 5th, minus when I plug in a 0, 0. So I just end up with 1/5 as my answer. So it took a really ugly problem and gave me a really good-looking solution right there. So if we want to double check that on our calculator, I go math, 9, and I'm going to integrate from 0 to pi halves. And my function is sine of x multiplied by cosine of x to the 4th power. Point 2, which is my 1/5. So again, you can't use your calculator on all of the questions, but you need to know how to use it. You can check your work, okay? All right, use the calculator because U substitution does not work. Sometimes it's not going to work very well, and you're going to, if it doesn't work, you're going to use your calculator, right? So for this one, like f of x, let f of x be an antiderivative of sine of cube x. If f of pi equals 5, find f of 1. So I like this question because it's saying big F of x equals the integral of sine cubed x dx. Okay. Now, I am integrating. It wants me to find f of 1, and it gives me f of 5. So here's what I'm going to do. I'm going to go from 1 to 5. I'm not going to do this by hand because it's really ugly and nasty. So I'm going to go to my calculator, and I'm going to do math integral from 1 to 5, and my function is going to be sine of x, but you have to make sure that you cube that on the inside, right? Sine of x cubed. When I hit enter, that's not 1 to 5. I'm going, wait, I put in the right numbers. No, 1 to pi. Sorry. 1 to pi of sine x raised to the 3rd. There we go. That looks better. 1.154393, blah, 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 blah. Okay, so this is equal to about 1.15439 something. But that's not my answer. That's what my derivative, or that's what my integral is equal to. But remember, if I was doing this by hand, if I was integrating, what I would end up with is I would take this integral. So I would take big F of the, why do I have a 5 right there too? Oh, F of pi equals 5. That's where my 5 came from. I'm going, what is going on? So F of pi minus big F of 1 would equal my 1.15439. So I found this integral on my calculator, but that's not my answer. That's just the integral. What it's asking me is, what is this value? Well, I don't know. That's what I'm looking for. But I know that, oh, no, that is the one I know. That one is 5. Come on, pen. That one is 5. I'm minusing f of 1, which is the one I don't know, to get 1.15439. So to get my answer, I'm going to minus 5 from both sides. So negative f of 1 equals some ugly number that then I'm going to times by, what is it going to be? It's going to be negative 3.8456-ish. And then I'm going to times both sides by the negative 1. So f of 1 is going to equal positive 3.8456. So a lot of times you use this U substitution and these integrals not to actually find the integral itself, but because you know that fundamental theorem of calculus, because right here I can say by the fundamental theorem of calculus, the integral is equal to big F of pi minus big F of 1. So I can use that to solve for other values. Now, integrating even and odd functions. Okay, so bottom line, an even function, if you don't remember what an even function is, an even function means, like if I were to take f of 2 and get some answer. So let's say it's 7. then f of negative 2 would also equal 7. If I were to take f of negative 4 or negative 3 and get negative 8, then f of positive 3 would also be negative 8. Basically, an even function, whatever's happening on the left and the right is happening on the other side. It's reflected over that y-axis, okay? So whatever's happening on the right is happening on the left. An odd function, if I were to have f of negative 3 equal to 2, an odd function would tell me that f of positive 3 is equal to negative 2. So an odd function is reflected, instead of being the same up above, it's reflected below. So it's reflected over this y equals, well, what would that be? That would be negative y equals x. So when it asks you, what's cool about this is if you have an even function, and if you look at it, again, I know these aren't to scale. If I have an even function, if I'm going to take the integral from negative 4 to positive 4, well, this area right here and this area right here, if I'm going from 0 this way and 0 this way, those areas are the same as each other. I don't have to do the whole integral. I can just find this part, and it gives me that part as well. I can just double it. So that's why the function says if it's an even function, you can go from 0 to a and just double your value. But if it's an odd function, look what happens. If I zoom in on my odd function, and again, I know I'm not to scale, live with it. If this is 4, if this is negative 4, then whatever's happening on the right above the x-axis is happening on the left below the x-axis. So whatever I get up here from 0 to 4 cancels out everything from 0 to negative 4. So the integral from negative a to a of f of x is 0. Okay? So looking at these functions, negative pi fourths to pi fourth of sine of x dx. The question is sine of x even or odd? And if you don't know what sine of x looks like, draw it. Go to y equals, let's put, oh look, we already have it drawn. Graph. That is an awful zoom. Let's zoom out. So what's happening on the right, if I'm at, well, let's pick that's a good number right there. That's like pi halves, right? If I look at pi halves, then this value is not the same on the other side at negative pi halves. It's the opposite. The positive over here becomes a negative over here. So that means that the sine function is an odd function. So whatever happens on the left and the right is going to cancel each other out. If I'm going the same distance, obviously if I'm integrating from negative pi to 2 pi, that's not going to cancel out. But if I'm integrating from the same values, if I'm going from negative pi fourths to pi fourths, they're just going to cancel each other out, and my answer is 0. Now the cosine graph, if I go back to my calculator, and if I graph cosine of x, it looks a little bit different. Let's get rid of that sine one. We don't need to see them both. My x values over here, my y values match my y values on this side. It's reflected. So if I'm going from 0 to pi, pi halves, this way, I get the same amount as if I go from 0 to negative pi halves. So for this one, I can say that I can just take double the integral from 0 to pi fourths of cosine of x dx. So if I integrate cosine, then I get negative sine. Nope. I'm going backwards, so I get positive sine of x. But I've got to go from 0 to pi fourths. So I get 2 multiplied by, what, root 2 over 2 minus 0. So those are going to cancel, and I'm just going to end up with root 2 as my answer. So let's check that. Let's do second calculate. I want to calculate my derivative from negative, whoa, what just happened? Second calculate my integral from negative pi fourths to positive pi fourths. And it gives me 1.41421. So 1.4121, blah, 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 something like that. What is the square root of 2? Second square root. If you don't have this one memorized, 0.14 or 1.41, which looks like what we had on our graph, except for that it's gone now. Hey, it still shows me the picture of it, but it doesn't give me the value. Rude. That's all right. I think we can survive with that one. Okay, so as far as your homework goes, again, this one, we might end up combining these two together so we have a day to kind of work on stuff without testing on the last day of the quarter. But do what you can at home, but know that coming to class will answer all the questions that you have. We'll work on these problems together.